This video is another in the series for Math 1224 for UTSA. Today we're talking about 5.6, the ratio and root tests. So breaking with previous patterns where I would do an example and just show here's how you do it, and then I would give the test, I decided in this video we'll just give the test first and then go through examples of using it. So the ratio test, if you have a sequence, A sub n, where all of the terms are non-zero because you're going to end up dividing by each of them as you go, let rho, that's this guy here, it's a Greek letter. It looks like a P, but it's sort of an italic P looking thing. Let that equal the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So you take the ratio of the two terms and putting the later term in the numerator and the prior term in the denominator, and you look at the limit of the ratio of the pairs of terms as n goes to infinity. Okay. In essence, you're looking at from term to term, do the terms get smaller, and do they get smaller consistently as you go along? Basically, smaller in size because of absolute value. So if rho is between 0 and 1, not including 1, then the series, as n goes from 1 to infinity of a sub n, converges absolutely. If rho is greater than 1, or if rho is equal to infinity, which is a little odd because infinity is not a number, but up here I never said that rho is a number. Rho is just whatever the limit is. And in the case that rho is infinity, the limit is infinity. Well, it's not a number, but it's infinity. Okay. Then the series diverges in that case. If p equals 1, then the test is inconclusive. You don't get a result. The series may be convergent or may be divergent. You don't know at that point. You have to try a different test, essentially. So let's look at our first example. And for these examples, I'm not going to start necessarily by doing the nth term test, although you might want to always do that anyway. Just start with the nth term test. As n goes to infinity, where does the sequence of terms go? Because, if they don't go to 0, then the series diverges. I'm not going to bother doing that with all of these. With this one, though, I will do that. I'll say, okay, what is the limit as n goes to infinity of 2 to the n over n factorial? And probably you've seen n factorial before, but in case you haven't, in case this is unfamiliar, or just if you need a reminder, if I write 5 factorial, okay, this means 5 times 4 times 3 times 2 times 1. Of course, the times 1 is kind of redundant. So this will be 120 when you multiply that together. Okay, so 10 factorial will be 10 times 9 times 8 times 7, and so on down to 1. So n factorial, this is n times n minus 1 times n minus 2 times n minus 3, and so forth until you get down to 1. Okay. So you might think, well, what does this do? We can't try to use L'Hopital's rule because n factorial, if we try to turn this into a continuous function, we'd run into problems. A continuous function of a real variable. It's not that you can't do that, but that becomes incredibly complicated. So let's not do that. Basically, we want to think about what happens in the sequence of numbers. Let's do a couple of examples. So it would be A1, right? A1, if you plug in 1 for n, you'd have 2 to the first power over 1 factorial. Okay, so 2 to the first power over 1 factorial, that's going to be 2. Okay, in fact, let's write it this way. 2 to the first power over 1 factorial, this is equal to 2. Okay, then you're going to have 2 squared over 2 factorial. Or in other words, on bottom, you're going to have 2 times 1. Okay, so this is, of course, 2, right? Then we're going to have 2 cubed. Okay, and on bottom, we're going to have 3 times 2 times 1. At this point, we don't get 2. We get 8 over 6 or 4/3. But I'll write it as 8 over 6. We'll leave it like that. Then we'll get 2 to the 4th power. And you start beginning to see where this is going at this point. In the first case, I'm going to rewrite the bottom, actually. 1 factorial is just 1, right? 1 times nothing else. So I've got 1 factor in the top, 1 factor in the bottom. In A2, I have 2 factors in the top, 2 factors in bottom. In A3, I have 3 factors in top, 3 factors in the bottom. In A4, I have 4 factors in the top, 4 factors in the bottom, which we haven't multiplied that out yet, but that's fine. We'll do that in a moment. So the number of factors in the numerator versus denominator stays consistent. It increases as we go, but they match, top versus bottom. In the numerator, all the factors are 2. In the denominator, as you go along, the new factor that shows up is 1 unit greater. So in the next term, the additional factor for the bottom will be a 5, and then after that, we'll get a 6, and then a 7, and so forth. Whereas the numerator just gets more copies of 2, okay? So, in fact, it may be useful to write it like that at this point. 2 times 2 times 2, 2 times 2 times 2 times 2, which if we want, what is that, 16 over 24? And maybe maybe it's kind of obvious that this first pair is the pair that we started with, 2 over 1. And then we had 2 over 2 as the additional pair in the next term of the sequence. And then 2 over 3, and then 2 over 4. Initially, we just had 2 over 1, right? Oh, and also should probably write this as 2 over 2, right? We just had 2 over 1, then 2 over 2, well, these are equal. So the size of the ratio didn't change. It's still 2, right? Then the new pair is 2 over 3. But now that the new element or new factor in the top is smaller, the new factor in the bottom is bigger, right? So we get something that's less than 2. Then we get another new pair, 2 over 4, and the bottom is larger. So we get a smaller result. So A5, so in A5, we're going to have 2 times 2 times 2 times 2 times 2 all over 5 times, 4 times 3 times 2 times 1, and the new pair is less than 1, right? 2 over 5 is a small number, less than 1. So the result is even smaller. So we get something like 32 over 120. And each term is successively smaller, right? So this limit is 0, okay? So I'm doing the nth term test for divergence just to check. I think now I'm going to try to get this out of the way. I might cut part of this out. Okay, so now we have room to try. Let's also move this. Okay, so now we have room to try the ratio test. Okay, but again, we won't do the nth term test for every example. I just wanted to do it for the first one. Okay, so we're going to want to find the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay. So we're going to, in the numerator, have a fraction with 2 to the n plus 1 on top and n plus 1 factorial on bottom. And then in the denominator, we'll just have this form with n as the exponent and the input of the factorial. So big fraction. So 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. Now, oops. Kind of important. The limit is n goes to infinity. Okay. I dropped the absolute value bars because all of this is positive anyway, so we don't need it. Sometimes you will, sometimes you won't. In this case, none of the terms are negative anyway. So I can rewrite this as when you're dividing by a fraction, you can rewrite this as the multiplying by the reciprocal of the denominator. So this is the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times, and I guess I should do something like that, times n factorial over 2 to the n. Okay, now I'm going to rewrite this, and what I'm going to do is I'm going to switch. There's just lots of ways to do this. I'm going to switch the two numerators. I'm going to put n factorial on the first fraction and 2n to the n plus 1 power on the second fraction. So this is the limit as n goes to infinity of n factorial over n plus 1 factorial times 2 to the n plus 1 over 2 to the n. Now, I think very likely you see where part of this is going, but the other part maybe not. So the part I'm sure that most people watch this will get right away is, oh, I can simplify this, because I can subtract the exponents, right? When you have a quotient of two exponential expressions and the bases are the same, you subtract the exponents. Or in other words, the numerator I could write as 2 to the n times 2, and then I just reduce the fraction, cancel the extra copies of 2. This one might be less clear, but it's kind of similar. So basically, the numerator says you're going to have n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And the bottom says you're going to have n plus 1 times n minus 1 times n minus 2 all the way down to 1. In other words, I guess I have some room right here at the bottom. N plus 1 factorial, this equals n plus 1 times n minus 1 times n minus 2 times dot 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 2 and then times 1. Okay, so every factor that is in the numerator is represented in the denominator. Okay, so in other words, rewrite this n plus 1 factorial as n plus 1 times n factorial. Okay, so here I'm going to have the limit as n goes to infinity of n factorial over n plus 1 times n factorial times 2 to the n times 2 over 2 to the n, and I get a bunch of cancellation. Okay, so I will have the limit as n goes to infinity of 2 over n plus 1, which equals 0 because the bottom grows without limitation and the top is just a number 2. So by the ratio test, this converges absolutely. The series converges absolutely. By the ratio test. All right. Okay, so the sum, or the series, or the sum, as n goes from 1 to infinity of n plus 1 all over 2n plus 7, or n plus 2. Okay, so the series as n goes from 1 to infinity of n plus 2 all over 2n plus 7. So let's go ahead and start the ratio test. And I didn't call it rho up here, but I'm going to say that rho, because that's what the test says we should be doing, but that's fine. This is the limit as n goes to infinity of a sub n plus 1 all over a sub n, well, the absolute value of that. Okay, so this will be the limit, so n goes to infinity of, big fraction, n plus 1 plus 2 over, let's do this, 2 times n plus 1 plus 7 all over n plus 2 over 2n plus 7. And I might, if I want, use parentheses to make this totally clear. So as before, when you are dividing one fraction by another, one rational expression by another, you can instead multiply the numerator by the reciprocal of the denominator. So this is the limit as n goes to infinity of, and I'll do some simplification. In the numerator, I'll have n plus 3. And by numerator, I mean in the numerator of the numerator, I guess. In the bottom of the numerator, right, I'm going to have 2n plus 2 plus 7, so 2n plus 9. Times 2n plus 7 over n plus 7. Plus 2, rather. So what to do here? Well, one way to do this is I could use the product rule for limits if I wanted to. I don't have to do that. So let's say the limit n goes to infinity, and I'll just FOIL the numerator, n plus 3 times 2n plus 7. So I'll have 2n squared on top 2n squared plus 13n. I believe that's correct. Plus 21. On bottom, I'll have 2n squared uh, plus 13. And again, plus 18. I think that's correct. Okay, that seems right. Okay. So, since n is going to infinity, these lower degree terms don't affect the results. This is the limit as n goes to infinity of 2n squared all over 2n squared. I can cancel the n squared factors, so I get the limit n goes to infinity of, well, 1, right? Which is, of course, 1. So, this is inconclusive. In fact, I should write ratio test is inconclusive. Okay. If rho is 1, then the test says, I don't know. So we have to try a different test. I could try if I wanted. I could try the integral test. I'm not sure if that's the best option to go with, but I could try it. I could try any of the other tests. But since this one didn't work, I'm going to revert to what we really should be trying. Maybe initially we should consider it. Again, this will be my summary later. The nth term test. So what is the limit as n goes to infinity of n plus 2 over 2n plus 7? Well, the 2 and the 7 don't affect the results. This is the limit n goes to infinity of n over 2n. I can cancel, and I get that this is the limit as n goes to infinity of 1 half. So I get 1 half. So by the nth term test for divergence, it's a pretty bad S there. For divergence, the series diverges. All right, so I could have done this first if I had thought to do it first, but of course this video is about the ratio test, not about the divergence test. So I wanted to start with the ratio test. And in particular, I chose this example so you could see what does it look like when the test is inconclusive. If we only have examples where the test is conclusive, well, then you might get confused on a homework or a test or whatever, where this happens if I haven't shown you this is what it looks like. Anyway, next example. Okay, so this one, it's got a lot of ends going on. So we're gonna, as you know, predictably, we're gonna use the ratio test. So this one has a bunch of ends. There's no other numbers, but we're gonna try the ratio test. So rho equals the limit as n goes to infinity of the absolute value. In fact, I don't need to write that large. Absolute value a sub n plus 1 over a sub n. Since everything here is positive anyway, I'm going to drop the absolute value bars in the next step. So limit as n goes to infinity of big fraction n plus 1 to the n plus 1 power over n plus 1 factorial, all over n to the n power over n factorial. So as before, I'm going to rewrite this as with multiplying by the reciprocal of the denominator. So this is the limit as n goes to infinity of, of n plus 1 to the n plus 1 power over n plus 1 factorial, which we will probably, well, we will be using the same trick where we rewrite n plus 1 factorial as n plus 1 times n factorial. I'm not going to do that yet. Times n factorial over n to the n power. Now, you might notice that this expression, the bases are not the same. That might present a problem for us, but we'll see what happens. We're not going to be able to do the exact same trick that we did with the 2 to the n. That's not going to work in this case. We'll have to do something else. But again, I'm going to switch the order of the numerator and denominator and see how it goes. So this equals the limit, rather, switch the order of the two numerators is what I meant to say. So the limit as n goes to infinity of n factorial over, and I'll go ahead and write this denominator as n plus 1 times n factorial times n plus 1 times n, or rather to the n plus 1 power all over n to the n power. Okay, so I get some cancellation, and it might not be clear what we should do next. Maybe you should pause the video and think about it. I noticed that this n plus 1 and this n plus 1 are the same thing. So maybe I need to rewrite this numerator on the right as n plus 1 times n plus 1 to the nth power. So this equals the limit as n goes to infinity of, well, I guess I'll write this as 1 over n plus 1, might as well. I'll write this as 1 over n plus 1 times n plus 1 times n plus 1 to the n plus 1, n power, not plus 1. That's kind of what the point of what I'm doing here. All over n to the n power. Okay, so this equals, because I get some cancellation, right? I get, this is the limit. N goes to infinity of n plus 1 to the n power all over n to the n power. Okay, and you might think, okay, it's not clear that we've accomplished much here. We've canceled basically everything that was present. All the factorials are gone. How about that? The factorials are all gone, so that's nice. Maybe it appears like we can't cancel anything else. These bases are not the same, so what can we do with that? Well, what we can notice is that this exponent is the same, right? Previously, this exponent was different, n plus 1. Now they're both n. These are both n. So I can write this as the limit as n goes to infinity of n plus 1 over n to the nth power. Right? You might be familiar with this. You might be starting to see where this is going. This is equal to the limit as n goes to infinity of, well, 1 plus 1 over n to the nth power. Okay, all I did was I took these two numerators and separated them into two fractions, n over n plus 1 over n. Well, either you see what's going to happen, like, oh yeah, I remember that I know what's going to happen here, or you don't. Now, I'm not going to go through the whole process. This is something you saw in Cal 1, so I'm not going to go through the whole process. But basically, this equals E. Okay, E is, you might, so quick refresher. This is similar to the A equals P times 1 plus R over N to the NT power. Right, that's compound interest formula. And as N goes to infinity, right, this will be P e to the RT power, right, as N goes to infinity, continuous compounding. So just quick refresher, and how do we know that? Why is that the limit? Well, that's a Cal 1 thing. Anyway, so we get a number that is greater than 1. Rho is greater than 1. Okay, so this means that the series diverges. So by the ratio test, the series diverges. Okay. So we had an example where we got convergence. We had an example where we had no conclusion. We had to use a different test. And then here we get an example where the series diverges. Potentially, maybe you could use since it diverges, the nth term test, it's not obvious to me that that would be easier, though. So, in this case, the nth term test, while it would be applicable, I'm not sure that that limit would be easy to do versus this one, because we were able to get rid of all the factorials through cancellation. That's why this one was more doable. Okay, what's next? Okay, so now we have the root test. So given a sequence a sub n, which does not have to be non-zero terms, you could have zero in your sequence. Let rho equal the limit as n goes to infinity of the nth root of the absolute value of a sub n. So basically the index of the root will increase as n increases. So you'll have basically a1 would be the first term, or the absolute value of a1. Then you'll have the square root of the absolute value of a2, then the cube root of absolute value of a3, and the fourth root of absolute value of a4, and so on. And the conclusions are basically the same as the ratio test. If rho is between 0 and 1, not including 1, the series converges absolutely. If rho is greater than 1 or rho is infinity, then the series diverges. If rho is equal to 1, then the test is inconclusive. Okay, first example. So the series as n goes from 1 to infinity of the quantity 2n plus 1 all over 3n minus 1 to the n power. Whenever you have an exponent of n, that's a clue that maybe you want to use the root test. It's something you should try. So limit, or rather I should say rho equals the limit as n goes to infinity. Rho equals the limit as n goes to infinity of the nth root. And I noticed that these terms are all positive anyway, right? So I don't need to worry about absolute value in this case. 2 to the n plus 1 over 2 to the n. 2n plus 1 over 3n minus 1 to the nth power. Since in this case, we didn't need the absolute value bars because everything's positive anyway, but if we did, we'd have absolute value bars. So the n's just cancel because everything inside the radicand is positive. Everything inside the exponent of n is positive anyway. So this equals the limit as n goes to infinity of 2n plus 1 over 3n minus 1. And of course, the plus 1 minus 1 are too small to affect the result. So this is the limit as n goes to infinity of 2n over 3n. I get some cancellation. And so I get 2/3 as a result. So the limit as n goes to infinity of 2/3, which is of course 2/3, which is less than 1. So we get convergence. The series converges by the root test. Okay. So let's go to the next example. So this one, I have an exponent of n in the top and in the bottom. It may be, well, 3n, but n is present in the exponent. It may be, in some cases, maybe even many cases, that you could use the ratio or root test. So I suspect we could use the ratio test here, but let's not. Maybe we could, but let's not. Let's use the root test. And notice that everything here is positive. We don't have to worry about minus signs. So rho equals the limit as n goes to infinity. And in fact, you know what I'm going to do? I'm going to observe here that 2 to the 3n power, this could be written as 2 cubed to the n power, or in other words, 8 to the n power. Okay. So this, the limit of the nth root of n to the nth power over 8 to the nth power, well, this will be the limit, as n goes to infinity, of the nth root of n over 8 to the n power. And now I get cancellation of those exponents. So this is the limit then goes to infinity of n over 8. The top's going to infinity, so we get infinity. So rho is infinity, so the series diverges. By the root test. Okay, next example. All right, so we have an exponent of n, and if I want, you might say, yeah, but the top doesn't. Well, 1 to the n power is 1, so I can just throw it on there if I want to, right? So rho equals the limit as n goes to infinity of the nth root of, and I'll cut to the chase here a little bit. Again, everything's positive. 1 over n to the n. This is, of course, 1 to the n over n to the n, as we just said. And since the exponents are the same, I can write this as 1 over n the nth power. Okay, so this is 1 over n the nth power, and now my exponent, my root cancel. So I get the limit n goes to infinity of 1 over n. And you might make an error and say, oh, this is harmonic series. That diverges. But we're not considering a series. We're considering this limit right now. Okay, so not a series. And if the bottom goes to infinity, then the whole thing will go to 0. So that's less than 1, right? So the series converges. And probably there are other tests we could use. In this case, like I said, ratio test. Maybe we could do a comparison test, either a direct comparison or a limit comparison. There are probably several tests that work for this example. So the series converges by the root test. Okay. Do we have another example? I think we do. Yeah, we got one more. Okay. So same thing. Let's try the root test. So rho equals the limit as n goes to, and you know what? N can't start at 1. N's got to start at 2 because ln of 1 is 0, and you can't divide by 0. So n equals 2. So as n goes to infinity of the nth root of square root of 1 over ln of n to the nth power. Okay, so this can be rewritten as the limit, because the numerator is also 1 is 1 to the n power. The same thing we did in the previous example. Then goes to infinity of the nth root of 1 over ln of n to the nth power. So my root and my exponent can cancel. And I get that this is the limit as n goes to infinity of 1 over ln of n. Okay. And so since if you think about the graph of the natural logarithm function, or just the behavior of logarithms, the bottom goes to infinity, so the whole fraction goes to 0. So again, the series converges by the root test. I think next is the summary. Yeah. So here's a convergence test strategy, a general strategy. How do you know which test to use? So if you suspect divergence of the series, use the nth term test, and that may be the easiest way to show divergence. If you have an antiderivative of essentially the sequence as a function, right? If you replace n with x, and then now you've got a function that matches the sequence, and check the premises of the theorem, the function would have to be continuous and decreasing, right? Past a certain point on a certain domain. So then try the integral test if you have an antiderivative of the sequence treated as a function of a real variable. If your series is similar to a known series, like a p series, for example, use a comparison test. There we go. Let's just pretend that didn't happen. If you see a factorial, use the ratio test. That's probably going to do it. Maybe not, but probably. If you see a power of n, try the root test. And sometimes factorial, sometimes the ratio test will work if you have a power of n. And there may be series for which more than one of these works. There may be series where 2 or 3 different tests work, but one might be easier than another. So I would check for them in this order. I think this is probably this is the order I would consider the options in, basically.